From this class until the end of this semester, we study thermal physics, and a famous physicist Boltzmann introduced the idea of a statistical description of thermal physics. So we will end up with elementary concepts of statistical physics. So elementary particle in thermal physics is molecules or less, smaller particles. In in physics, there are various fields, but is a very special. The statistical physics is a very special field uh, that deals with the behavior of matter when the number of participants increases to a very, very large number. To us, it is almost infinity. A unit of a large number can be, it is subjective, although it's a subjective. A large number in this physical system is Avogadro's number. It's a huge number, 6.0 times 10 to the 23rd. Okay, it used to be an approximate number, but now it is exactly defined to be 6.022140076 exactly. Okay, so we will find what this mole means in practical use. The thermophysics works for macroscopic states, but as we make a transition to statistical physics, then it extends all the way down to the subatomic level and elementary, genuine elementary particle that is dealt with elementary particle physics. In nature, there are two kinds of particles. One is boson, and the other is a fermion. It This classification of elementary particle for boson and fermion is a statistical view, and it is closely related to the spin. Until now, we learned angular momentum, and angular momentum was only for the orbital motion that requires explicit transition from a specific point to another point. Therefore, the orbital angular momentum is defined by L, that is x cross p. X is the position vector, and p is the linear momentum vector. However, people have found that there is another angular momentum that does not involve the motion from a position to another position. That strange angular momentum was found in quantum mechanics for elementary particles. For example, electron rotates around the nucleus in an atom, and it does have the orbital angular momentum because its position is non-zero. Is if we consider if we allocate the origin of the coordinate system at the center of the nucleus, then the position vector is non-zero and its linear momentum is non-zero. So x cross p, the orbital angular momentum, is not zero. If orbital angular momentum is zero, the atom must collapse. There's no way to have a minimum value for the potential energy that we just learned when we studied Kepler's three laws of motion. Anyway, it was found to be there must be a quantum number that represents the angular momentum, but that is not the orbital angular momentum. That is called the spin angular momentum. It was discovered by the in combination with Pauli exclusion principle that the allowed energy level or allowed state, quantum mechanical state for an electron in a hydrogen atom system uh, with the same quantum number, except for this now known to be spin quantum number. Electrons are not allowed to have exactly the same state, while the boson, such as a photon of such as photon, that has an integral multiple of spin states. The fermion has a half integral, so one half, three halves, something like that. So boson has a 0, 1, 2. Anyway, we cannot spend too much time on this. But anyway, if you go down all the way through the elementary particles, we have to consider the quantum mechanical effect, and at that level, the statistical uh, classification for two kinds of elementary particles is uh, crucial, and in nature there are bosons or fermion of elementary particles, either boson or fermion. And boson has an integral multiple of spin state, and spin quantization number is an integral number, and fermion is a half integer, and boson has identical boson may have identical states. However, identical fermions are not allowed to have exactly the same state. That's of absolutely different nature. So boson has a symmetry of exchanging any two bosons, identical bosons. The fermion has anti-symmetry when we exchange the two particle states. Okay, so statistical physics is a very interesting physics. Unlike the other parts, it deals with a very large number. And the main issue will be the central limit theorem. That when the number of particles increases, so average of some state variable uh, is concentrated the central value. So we will study as we go further. Okay, matter, substance, elementary particles. Okay, there are particles that forms the matter, and matter, if you divide any matter, you will find a single uniform substance. And that single uniform substance consists of a same kind of same kind of elementary particles called atom. An atom consists of nucleus and electrons surrounding them. And nucleus is composed of nucleons. And nucleons are called either proton or neutron. So nucleus is a very tiny object. In it there are positive charges, that is called the protons, and electrically neutral particles, the neutron, are placed. And outside there are electrons. Electrons are electrostatically negative. And as I already told you, the positive charges repel very extreme force. They share extremely large repulsive force. So it is, oh, if there is only electromagnetic field, then we cannot describe the stable nature of atom. However, there are another forces. There's nuclear forces that is called strong or weak interaction that makes the nucleus stable. In addition, any proton and neutron are composed of three quarks. For example, proton consists of up quark, and down quark. And up quark has electric charge, two-thirds of electric charge positive. A down quark has one-third negative of electric charge. Very strange, right? So the nature has a very systematic building block. In order to consider thermophysics, we mostly uh, consider molecules. And when we describe molecules, then we need to use the atomic symbols. The typical standard way of writing an atom is this X means that this is atomic symbol. This represents the atom. And this atom consists of nucleons, and nucleons are protons, either protons or neutrons, and their masses are approximately, not exactly, approximately the same. They are similar in mass, so we have two kinds of number, A and Z. So A is called the mass number, and Z means atomic number. Atomic number represents the number of protons inside the nucleus. This is the most important one. The Z, number of protons, determines the nature of an atom. But for a given number of Z, there are mostly A is fixed, but there are rare cases that is not the same as the average value. So number of neutrons may differ atom by atom. So chemically, we use the average value of A for measuring actual mass of an atom. But for a single atom, number of neutron is fixed. So this mass number is just the sum of number of protons and number of neutrons in a nucleus. And Z is always fixed for a given X. So if I know X, then Z is definite. I don't have to write, but there are so many elements. So usually we put the number Z, atomic number, in here explicitly. And we have to write the mass number to identify what the actual atom is. So there are several atoms with the same atomic number but different mass number. Okay, I told you nucleus is a tiny and it depends on the number of protons or neutrons, not linearly. Anyway, for example, a hydrogen atom has nucleus that is proton, single proton. It is a very tiny number. So femtometer, F, F named after Fermi. Uranium, it's a much bigger. It has a very large number of nucleus inside the nucleus. Okay, we learn how to write atomic symbols. Mass number, that is a sum of number of protons and number of neutrons in the nucleus. A Z is definite for each symbol X, and that represents the number of protons. If an atom is electrically neutral, then the number of electrons will be the same as the atomic number, Z. In nature, most most molecules are electrically neutral. For example, uh, hydrogen molecule is the molecule atom itself usually is less stable than molecule. So if it is if it has just a simple sum of two energies, if if the if there is a way to bind them, there is attractive force, right? Just like two massive particles under gravity, they have orbital angular momentum and they are making an orbit. So it is a kind of composite particle system. Why don't we replace this gravity with the electromagnetic field and replace it with charge, positive charge and negative charge? Usually, due to the attractive force, that they collapse, they approach forever. However, if there is angular momentum, the potential energy naive potential energy is decreasing forever to make them collapse. However, if they have orbital motion, non-vanishing orbital angular momentum makes the problem to for radial problem, seeing one-dimensional radial problem, and we have found that effective potential energy in the one-dimensional problem makes the minimum value. So there's some stable point, and this is a circular path in the uh, classical mechanics, right? And it is an elliptic orbit and parabolic orbit and the hyperbolic orbit. Parabolic and hyperbolic we are interested in when we consider a stable system. Stable system is a bound system. So if two hydrogen have some interaction potential, effective potential energy like that, then they can make a bound system at some point. That is a molecule. So rather than this is a free particle, and if the energy is lower than the free particle state, there exists a bound system. So that bound system is called molecule. All right, and molecules are not uniform, right? Because they have nucleus, nuclei, for example, proton, two nuclei and electrons surrounding them. So this is composite system. So we have not uniformly electrically neutral. Instead, we have some positive charge inside and negative charge inside, and they have a certain distribution, at least probabilistically. So it has an intrinsic nature of dipole or quadrupole and so on. Because of that, this monopole interaction is called the Coulomb interaction, that whose force is 1 over proportional to 1 over r squared. If we have dipole, they are not separable, but instead the total is electron neutral. However, partially positive and partially negative, so that the net sum of the electric charge is vanishing. In that case, just like a magnet that has the two magnetic charges, north and south pole, they they interact, they align. This kind of nature, dipole nature, in molecule, a collection of molecules is called van der Waals force. That is dipole-dipole interaction. So even the electrically neutral, for example, H2O, this water molecule, they are positive and negative parts are distributed asymmetrically, so they generate a dipole moment. And just like a magnet, they have a binding force among molecules. Okay. Another elementary particle in thermophysics as well as chemistry is ion. This atom that lost some of electrons, electrically neutral state. From this electrically neutral state, if it loses some electrons, it becomes ion, and ion has electrically charged. So its electric charge generates the electrostatic interaction. In nature, there are three kinds of phase. Three kinds of phase you're well familiar with: solid, liquid, gas. Let me pass just to read it through. So the three phases depends on the the dominant binding force and the interaction among the molecules. Perhaps the solid state has the strongest bound binding energy, and the liquid, it is a little bit loose, gas almost free. Let's just read it for fun. This is actually the beginning of this lecture. The temperature. What is temperature? When we study the system of particles, the total mechanical energy is the sum of the total kinetic energy and total potential energy. And total kinetic energy was expressed in terms of center mass momentum square over 2m, where m is the total mass of the system of particles. And for example, two-body system, we had this kind of form, is a reduced mass. And what is that? This is internal kinetic energy. And that internal kinetic energy is the sum of the kinetic energy of any particle bar means relative xi bar is a relative position, the position relative to center of mass. So if we consider system of particle at the center of momentum frame, this one vanishes and this internal kinetic energy survives. And if we have many system of particles, for example, we consider collision of two rigid body, then after the collision, sometimes they make an inelastic collision. In that case, the lost energy is not really lost, but it is not observed because it has been transformed into microscopic motion as the internal kinetic energy. Thermophysics is really concerned about this internal energy. And we define the average kinetic energy of the system of particles at center of momentum frame is to be the temperature. And temperature is just exactly the same as kinetic energy, average kinetic energy, except that there is a proportional constant called Boltzmann constant. Okay, temperature is the average kinetic energy with the scaling factor Kb, that is Boltzmann constant. And we always consider at the center momentum frame. So this one is ignored. Only the relative motion with respect to the center of mass is concerned. And the unit of the temperature T, is Kelvin. Because this is the kinetic energy, sum of kinetic energies at the center of momentum frame, every kinetic energy is a positive definite. The minimum value should be zero. There is a every contribution is non-negative. So what is possible? We have a 0k, that means absolute zero indicates that there is no motion at all at the center of momentum frame. That represents the temperature 0k Kelvin. Next, we consider thermal equilibrium. Now we already entered into the space of statistical physics. If we have a very large number of particles, when we describe the temperature, then that the temperature is average kinetic energy of every molecule consisting of a sample of, for example, gas. The temperature is the average kinetic energy. Okay. If a thermal system is in equilibrium with the temperature T, that means every particle has this kinetic energy approximately the same as the average value. So it is a very rare to find a molecule that has the kinetic energy that is far from its average. In that case, that we call it thermal equilibrium. Is it possible? For a single particle, it's possible. If there are 2, 3, 4 particles, it's not easy to imagine. It is a very narrow window to have everything all together, to have its own kinetic energy. to be the same as the average value. For example, you take the exam, 100 number of students took an exam, same exam, and there is a distribution of points, and it is almost impossible to have everybody has 50 points. Suppose that we have the average value of the 50. The the reason is that it's the number of students are very very small in comparison with Avogadro's number that is of order 10 to the 23rd. A huge number, enormous number. In that case, if every student do not take care, for example, the exam was an O or X problem, and students just choose either X or O, the average value will be 50%. That's right. But if only a few students took an exam, the distribution should be wide. But in case we have 10 to the 23 or more, or 10 to the 100 and 10 for 1 million, enormous number, the average is still 50%. However, the distribution becomes a very narrow. You will find it is a central limit theorem, and for a very large number of samples, then if the sample consists of a very large number, then the distribution will be concentrated at the center if if any participant are of equal probability to choose O or X. If everybody is not identical and each person has its own will or some specific intention that has different character, then the distribution may be wide. But what we consider in this the thermophysics, that every molecule is identical, and there is no special molecule among 10 to the 23rd uh, molecules consisting of a sample. So left one, right one look similar, but they are well separated. Red balls and sky blue balls, they are well separated. And this one is much more mixed in comparison with the right side. The probability of finding this kind of state is much greater than these well separated cases. We shall find in with an explicit computation that this one has a more probability. So in thermal physics, at the end of 28, X28, you will find the entropy theory, and this one has a more entropy. More probability means a more entropy, larger entropy state. So when the number of participants increases, there's a strong tendency of time flow. So at some point, it is possible to observe this kind of specific state, but as time goes on, the statistical system make a transition always to the more probable states, such as the left-hand side. Zeroth law of thermodynamics. Until now, we have considered the equilibrium state, and equilibrium state involves a very large number of molecules, very large number of elementary particles in statistical physics, and when the number it becomes very large as time goes on, the average, the average state will represent the anyone's state. I mean, the separation of a specific state from the average state decreases very rapidly as the deviation from this average value increases. So, on the thermal equilibrium, the two we we let the two objects with the thermal equilibrium connected and let them share their heat energy. So heat energy is the total internal kinetic energy of the two systems. And there is a rapid collision of molecules on the A side and B side. As time goes on, the kinetic energy will be shared by the two samples in A and B. And if you have enough time, then the kinetic energy of the two systems will be equivalent, average kinetic energy, I mean. And that is independent of the mass of each molecule. That is a very interesting. Heavier objects, heavier molecule moves slowly, but not the momentum, but the kinetic energy is averaged over. And average kinetic energy is the same for any mass. Anyway, if A and B are in equilibrium and B and C are in equilibrium, thermal equilibrium, the two temperatures are the same, two temperatures are the same, and finally, A and C can make a thermal equilibrium. So A equals B, B equals C, A equals C. These two conditions requires A equals C. In mathematics, it is just a trivial problem. But in physics, if I can say A equals B in temperature, it means the average kinetic energy of a system is the same as the average kinetic energy, internal kinetic energy of the system on the right side. So it looks very simple, but it is not really trivial problem. 0 Kelvin. I already told you the temperature is in units of KB, that is called the Boltzmann constant. Boltzmann created the statistical physics. The thermal physics is now understood as a statistical viewpoint, and the statistical view is the average kinetic energy of a single molecule is the temperature in units of Boltzmann constant. That is the just very nice example of a statistical view of thermal physics. A long time ago, they used the triple point of water to consider reference temperature, and from this they measure the absolute temperature. But a physically correct definition of absolute temperature, that K 0 K is just the absolutely vanishing kinetic energy of the whole system relative to the center of mass. That is exact. Again, Boltzmann constant 1.380649 to the 10 to the minus 23rd. This is the exact number without error. Remember, this is exact. People use this is closely related to chemistry. There's a Charlotte's law. Charlotte's law is if a gas sample has a fixed number of molecules, it's it's a fixed volume. if you increase the temperature by heating the system, then pressure increases. That means heat energy is transformed into the kinetic energy, right? Heat is energy, and the transport into the kinetic energy of molecules. If the kinetic energy of molecules increases, it becomes faster, and as a result, pressure increases. But right now, it is the proportionality of temperature, absolute temperature, and pressure is experimental result. Charles' law is not deduced from any theory. It is just the experimental phenomenological result. And at the later in this course, we will find that ideal gas theory reproduces the Charles law as well as the Boyle's law. And finally, we obtain the ideal gas equation using kinetic theory of statistical point of view. Perhaps the United States is the only country use a very strange unit system for temperature. They are so isolated from universe. They are still using Fahrenheit, a very strange temperature. If you read some article, it originates from the reference temperature for the Fahrenheit is related to cow. So search it, and why don't you Googling the Fahrenheit and cow? Then you will find a very strange basis of this strange unit system. But except for the country that use Celsius, including Korea, and practically, if you travel United States, you when you watch a weather forecast, you have to translate the temperature in Fahrenheit to Celsius in either direction. So these are useful practical formula just to memorize for uh, your life. Next, we consider thermal expansion. If an object acquires heat, then the kinetic energy should increase. So as temperature increases, usually the solid state vibrates. The elements of elementary particles of solid states vibrates, and they need more space between them. Because of that, at high temperature, solid expands. But this is a case of linear expansion. If you give a temperature increase, then you will obtain some change in length. You will find this is a length change per total length. This is closely related to Young's modulus of bulk modulus, right? It is just a kind of strain. Fixed strain appears depending on the temperature change. So this alpha, coefficient alpha, is called linear expansion. And you find this kind of shape on every bridge. If this is in winter, they are shrunken, the gap is wide, and the, when it is very hot, they are expanded to fill the gap. If there is no such kind of the structure, then the bridge will break down. Uh, there will be cracks, and the structure will be unstable. So it is a very important. And you also find the power lines from the power plant to cities, the long wire, the copper wire is very expensive. However, in summer they are bent, and winter they are tightened because of the change in the length in the due to the thermal expansion. Thermal expansion is three-dimensional. So if it is just a straight wire, the length increases and the cross-sectional area also changes, but it is not noticeable. However, the area or volume is sizable. You can see what happens. The symmetric nature of the expansion can be applied to change in the area, and the expansion formula will give there is a double factor. Factor of 2 appears for the area expansion, and for the case of volume, if you expand, you find the leading contribution is a factor of 3. So coefficient of volume expansion have a factor of 3, and the area expansion factor of 2. It's a simple algebra. We have repeatedly talking about the temperature, and temperature is the average kinetic energy of molecules. So heat is equivalent to energy. Heat capacity and specific heat. Heat capacity is just if you supply heat delta Q to a system, and the system has the average kinetic energy increase by delta T, the temperature, then the ratio of heat per unit temperature change is called heat capacity. Heat capacity is proportional to the amount, how many particles are there, uh, how heavy are there. So it is a proportionality constant. So we use a small c, it is not speed of light. So per mass is called specific heat. Heat capacity per unit mass is called specific heat. Again, one more is Avogadro's number. This is the exact number. Nobody will count the number. It is almost impossible to count this number. Heat of transformation. We have three phases: solid, liquid, and gas. And a sample of n molecules make a transition from a phase to another phase. It requires energy to break the bondage, or it requires energy to let them bind together. I mean, binding energy between two molecules in solid is the strongest, and liquid is less, and gas is almost no. The gas is almost free. So bring two, for example, bring two particles, they are free. Let them be close together to become liquid. We need to pull out the kinetic energy from the gas state. Again, in a similar manner, from liquid to solid, we need to pull out the energy from that one. In reverse, if you want to make melt the ice to water, then you need to pour some energy by heating the system. So suddenly at this given temperature, for example, 0 degrees, at they need some energy to change its shape from solid to liquid. So there's a latent heat, and it is in general it is called the heat of transformation. And heat of vaporization is, for example, per unit mass is 539 calories per gram of water, and heat of fusion is about 80 calories per gram. We have some exercise. We have two samples of thermal system with heat capacity Ca and Cp. It was in equilibrium, thermal equilibrium at temperature Ta, and Cb, capacity Cb, was in a thermal equilibrium at temperature Tb. If we mix them up and wait enough time to reach the total system to arrive at a thermal equilibrium with a temperature capital T, during this process, we assume that there is no loss or gain of energy. So the net exchange is a zero. I mean, the higher temperature object give away some heat, and that exactly the same amount of heat is transferred to the lower temperature sample. So heat energy is conserved. So this is the lost energy from the higher temperature object as a gained energy from the lower temperature object. If you simplify this, and you can find the final temperature T of the composite system. A similar calculation can be made if you have a transformation, heat of transformation. So latent heat should be used to consider this. So here, solid, this is A is a solid, and B is, it is placed in thermal contact with solid B. Okay, it has a latent heat of fusion, and then it is melted as a heat away. Okay, so there was a transformation. So latent heat L should be used to solve this problem. In comparison with the just the previous problem with the same phase, we need latent heat. In the remainder of this class, we have calculations involving log, integrals of log, and powers, including some arbitrary powers. So it is good to review some calculus idea. Exponential function has a base that is called the Euler's number. It is a 2.7 something, and there is no repetition of number. It looks for a very short time. It 8 appears very many times in comparison with many other uh, numbers. There is no repetition. We notice that we have 1 over n. This is a very tiny number. As n approaches infinity, it becomes a 0, but inverse power, there's an infinite number of power appears. So it is not trivial to have this kind of number. But you can make use of the binomial expansion to find this as a simplest case. For x equals a positive number, exponential function can be expressed as this, and I have copied this Euler's number definition in here and attached x. Why don't we multiply x in the denominator and numerator, and let nx equals m, so nx approaches infinity. In that case, this e to the x can be expressed in terms of this. And again, binomial expansion can be made to this to find and actually the Taylor series expansion of exponential function. The derivative of exponential can also be obtained from this definition. And by definition, the derivative of this function can be expressed by using this expression for the exponential function. I have substituted x plus delta instead of x in here, and substitute x as it is. And we can factorize this a to the nth power subtracted with b to the n, that is factorized. So with this linear factor appears, and the remaining factor is the exact factorization. And as delta goes to 0, this one is absolutely cancelled, and this is a finite one. And in the remaining factor, we can just substitute delta equals 0. I have made use of this factorization formula, and this limit is just 1 over n. And finally, this one, I can ignore this delta because the delta singularity disappeared in this ratio. So delta can be substituted. We can substitute delta for 0 for delta. Finally, we have this form. And why don't we multiply the same factor once and divide it by, and as n goes to infinity, this is just exponential. So exponential functions derivative exponential itself. And we can rescale the factor a, multiply a, then change of variable can be used to make use of the derivative of this is the same as this. And during the change of variable, I have multiplied and divided a in the numerator and denominator as long as a is not equal to 0. Then derivative of arbitrary factor a is an exponential function multiplied by a. And using this, I can generalize to the inverse transformation. Natural logarithm ln is the inverse function of the exponential function. So e to the y equals x, and when I substitute y equals 0, then this value is identically 1 according to, if I substitute a 0 here, it is identical to 1. And inverse relation, if we rewrite this one, so y equals log x, and this one gives a log 1 is 0, this is just a definition of the inverse function. Why don't you take a total differential of the left and right side, differential of exponential y, and it becomes a dx. Okay? And we divide this both sides with the dy. And this is a y, exponential y is y derivative itself. Okay, and then from this, I exchange this e to the y and dy, and differential dy over exponential y, this dy, and by making use of the fact that e to the y is x, then dx over x is d log x. Too simple. So that means I have an integral table. We have already known this e to the 0 is 1 and log 1 is 0. Therefore, 1 over x integral from definite integral of 1 over x from 1 is exactly log x. So this one can be made use of to find log a times b, and log a times b is by this derivation is integral of 1 over x from 0 to ab. And then we can divide into two pieces from 0 to A and A to AB. And we scale this variable, the changing variable, by multiplying A. Then the AA cancels in the numerator and the denominator. It is simply 1 to B integral. That is, according to our finding, is log B. As a result, if we substitute in here, log AB is always log A plus log B. If we can extend this idea to 8x to the 8th power and y to the bth power. The total differential will be like that. And the Leibniz rule, it can be used to separate the differential, and that each differential has a power behavior. Divide both sides with the z, this original factor. We have log style behavior. So differential of log z is this power a times d log x and b times d log y. These calculations will be used later in thermal physics calculation. So please review this exponential log calculation carefully. That's it for today. Thank you.